Welcome students, this is Ravi Shankar and today we are going to study about the electrostatic potential energy for the collection of point charges. So today we are going to study about electrostatic potential energy. Electrostatic potential energy for the collection of charges. First of all, let us consider for two charges what is the electrostatic potential energy, and after that let us extend it to three charges. So, in order to calculate the potential energy for the collection of electrical charges, generally how you can able to define this? See, we can state that potential energy is the work done in assembling the charges. Work done in assembling the charges. So the charges can be assembled inside an electrical field between any 2 points. That in general we are stating that potential energy is the work done in assembling the charges. Okay, how you can able to get? So, in order to get this equation, you consider a point charge. So, I am writing it like this. For a point charge Q1, for a point charge Q1, the potential at a point, at a distance r1 is given as potential is V due to the charge Q1 at a distance r1 is 1 divided by 4 pi epsilon 0 into charge is Q1, and if I am considering the distance as r, not r1, I am taking it as r. What is this potential? That is, if you are considering a point charge, then the potential at a point distant r is V is equal to 1 by 4 pi epsilon 0 into Q1 by r. What is this potential? We know that the potential is nothing but work done in moving an unit positive charge, work done in moving an unit positive charge from infinity to, from infinity to that point, that we are taking it as the potential at a point distance. Now, instead of moving this unit positive charge, if another charge Q2 is moved, what will be the work done? So, now let us take like this. Now, if a charge Q2 is moved from infinity to a point, then what is the work done? Then work done is equal to the potential V, that is the work done for moving the unit positive charge multiplied with the amount of charge moved. So this work done can be written as, instead of V, I can write the formula 1 divided by 4 pi epsilon 0 Q1 divided by R. This is potential multiplied with the Q2. Now this work done is stored as what? This work done is stored as the potential energy. So we can write this work done. Okay, now I can write this work done is stored as electrostatic potential energy. Electrostatic potential energy due to the two charges. Therefore, this work done. So potential energy is represented by epsilon is equal to 1 divided by 4 pi epsilon 0 into Q1 into Q2 divided by R, and measured in terms of an unit called to be joule. So from this we can say epsilon, that is the potential energy, depends on the distance between the two charges. Depends on the distance between the two charges. So based on this work done, the potential energy is defined. So using this we can state. How we can state? See, in fact we can state as potential energy is the work done in moving one charge from infinity to a point inside the electrical field, or we can say work done in assembling the charges. This equation will be true if Q1 is fixed and Q2 moved from infinity, or vice versa, Q2 fixed and moving Q1 from infinity, or take both Q1 and Q2 to infinity and move them from infinity to the two respective points. In all these three cases, this equation epsilon is equal to 1 divided by 4 pi epsilon 0 into Q1 into Q2 divided by R. This equation epsilon is equal to 1 divided by 4 pi epsilon 0 Q1 into Q2 divided by R. This equation will hold good. Let us consider what? Let us consider the definition. So we can write in fact. Okay, I can write. So I can consider like this. See, in fact, okay, in fact, the work done in assembling the charges, okay, we can write like this. In fact, potential energy is defined as work done in assembling the charges, Then second point, this equation that we have derived, this equation is true if Q1 is fixed and moving Q2 from infinity to the point, or Q2 is fixed and moving Q1 from infinity to the point, or moving both charges Q1 and Q2 from infinity to the respective points. In all these cases, the above equation, that is the above equation, epsilon is equal to 1 divided by 4 pi epsilon 0 into Q1 into Q2 divided by R hold goods. This is called to be potential energy due to two charges. If you are considering more than two, if you are considering three charges, how you can able to get the answer? So that was the next topic that we have to, the next concept that we have to study. So the next point is potential energy due to system of charges. What do you mean by this system of charges? Potential energy due to system of charges. See here, I am going to consider a system with the three charges. A configuration is being given. One of the point is A, another point is B, another point is C. At point A, there is a charge Q1. At point B there is a charge Q2 and point C there is a charge Q3. In between A and B, let us consider the distance as R12. Between A and C, let us take the distance as R13. Between this C and B, let us take the distance as R23. There is 2 to the charge Q2 to the charge Q3. So a system of charges is being given. What is the total potential energy due to this system of charges? See, a procedure is being given in your book. First of all, I will be dealing with the procedure that is given in your book, and after that I will be giving you a simple or an easier method. So according to your book, let us write. So to calculate electrostatic potential energy, of the given configuration, the following procedure is adopted. Okay, we are going to adopt a procedure. So I am writing the following procedure is used, or I can write is adopted. So what is that following procedure? See, what you have to do is, initially you consider that all the 3 charges are at infinity. Okay, you consider all the 3 charges Q1, Q2 and Q3, all the 3 charges are considered to be infinity. So by considering all the charges are infinity, first of all what I am going to do is, I am bringing the charge Q1 from infinity to the point A. See, when I am bringing the charge from infinity to the point A, around that point A there is no other charges initially. So no work is said to be done, because the charge Q1 is unaffected by the other charges. Since there is no other charges, the charge Q1 is unaffected. So the first point or the first procedure that I have to consider is, I have to take or I have to consider the charge Q1 to be brought from infinity to what? Brought from infinity to the point A. For that, no work is said to be done. So I am writing the first point that I have to write, that I have to consider. What is the first point? So I am writing like this: bring the charge Q1, from infinity to the point A. So in order to bring the charge Q1 from infinity to the point A, we can say no work is needed. Or we can say no work is done. Why? No work is done because no other charges are already present in the vicinity of Q1, nearer to Q1, in the vicinity, that is nearer, vicinity of what? Vicinity of Q1. So no work is said to be done. Okay, no problem. That is, from infinity, the charge Q1 is taken to this position. What is the next one? Now I have to take the second charge, or I have to consider the second charge to be brought. So the second charge Q2 is brought. So I am drawing the diagram here. See, already you are having the point A where the charge Q1 is brought from infinity. Now from this point I am considering another point here. What is another point? The other point from here is Q2 or B, which is at a distance R12. Now what I am going to do? Now I am going to bring the next charge Q2 from infinity to the point B. So the next charge here is brought here is Q2. But when Q2 is brought, this Q1 will produce an opposing electrical field. So a work is said to be done against that electrical field. Now we have to calculate what is that work done. So what is the second point? The second point that we have to consider is to bring the second charge. Okay, I am writing like this. To bring the second charge. What is the second charge? To bring the second charge Q2 from infinity to the point B, what we are in need of? A work must be done. We have to say a work must be done, because what is the reason? That Q1 will have an influence on this point B, and due to the electrical field there is a repulsion, because a work must be done against what? Against the electrical field produced by what charge? Produced by Q1. So the work done on the charge Q1, on the charge Q2 is, because Q2 is moved. So the work done on the charge Q2 is the potential energy stored. So potential energy or the work done is equal to, what is it is? The potential at point B due to Q1. So I can write potential is V at point B due to the Q1. So V1B multiplied with the amount of charge moved, which is equal to, what is the potential? 1 divided by 4 pi epsilon 0 Q1 divided by R12 multiplied with Q2. This is another form of the previous equation that we have studied. 1 by 4 pi epsilon 0 into Q1 into Q2 by R. So this is considered to be equation 1. Okay, this is the work done when you are moving Q2 from infinity to the point, and when you are doing this work done, or when you are considering this work done is stored as the potential energy in between the two charges Q1 and Q2. Now what we have to consider? We have to consider the next one. What is the next one? We have to bring the third charge. What is the third charge? The third charge is Q3. When you are bringing the third charge Q3, that is point number 3. Again, let us consider the diagram here. Here you are having the point A where the charge Q1 is placed. Then at a distance R12, you are having another point B where the charge Q2 is moved. Now you are having the third point C. See, the third point C is at a distance of R13 from Q1, and here it is at a distance of R23. If you are moving that Q3 from infinity to the point C, when Q3 is taken from infinity to the point C, a work is said to be done against the electrical field produced by Q1 and produced by Q2, because the point C is under the influence of the charge Q1 as well as the charge Q2. Clear? When you are moving the charge Q3 from infinity to that point C, then we have to state that work is said to be done on Q3 against the work or against the electrical field produced by Q1 and by Q2. So that is the third point. So third point is while, or we can write when Q3 is brought, when Q3 is brought from infinity to the point C, we can say work must be done. Work must be done against the electrical field. Work must be done against the electric field. Against the electrical field produced by Q1 and also by Q2. So then what is the work done? Now this work done on Q3 is also stored as potential energy on Q3, which is equal to, see what I have written, potential multiplied with the charge. First of all, potential at point C due to Q1, that is, we can write potential is V due to Q1 on C. So I am writing it as V1C plus the potential at Q3 due to Q2, or sorry, potential at C due to Q2. So that is potential due to Q2 is V2 and it is at the point C. So we can write it out as V2C. Since the potential is a scalar quantity, total potential at the point C is the algebraic sum of the two. What is the work done? Potential multiplied with the charge moved, that gives you the potential energy. See, let us write here. What is this V1C? V1C is potential at C due to what? Due to Q1. So what is potential at C due to Q1? It is 1 divided by 4 pi epsilon 0 Q1 divided by, what is the distance? The distance is R13. Similarly, what is V2C? V2C, we can state that it is nothing but, see, it is nothing but potential at C due to what? Due to the charge Q2, which is again equal to 1 divided by 4 pi epsilon 0 into Q2 divided by R2, 3. Now you have to simplify. You take these two values and substitute in the above equation to get the total potential energy. So therefore, this work done, this equation I am substituting the potential energy epsilon is equal to, taking Q3 out, I can say, see, on substituting, what is this V1C? It is again writing 1 divided by 4 pi epsilon 0 into Q1 divided by R13 plus 1 divided by 4 pi epsilon 0 into Q2 divided by R23. Okay, now you simplify. How to simplify this? Potential energy is equal to, take this constant as a common, 1 by 4 pi epsilon 0. Q3 taking into the bracket, I can write Q1 into Q3 divided by, what is the value? R13 plus then Q2 into Q3 divided by R23. So this we are taking it as the potential energy while you are moving Q3 from infinity to the point C. Let us consider this equation as equation 2. So totally we are considering what? Totally we are having two work dones. One for moving Q2 and another one for moving Q3. Now the total potential energy can be got by adding these two equations. Therefore, the total potential energy due to the system given, or due to the configuration, due to the system of charges is given by total epsilon U. See, this total potential energy is equal to adding equations 1 and 2. Adding equations 1 and 2. So add the above two equations. The total electrostatic potential is equal to, when you are adding both the equations, we will be getting finally as 1 divided by 4 pi epsilon 0 into, say, taken as common, In the first equation, you will be getting Q1 into Q2 divided by R1. First of all, it is R12 plus then Q1 into Q3 divided by R13 plus Q2 into Q3 divided by R23. So this equation represents the total potential energy due to the system of charges. Any doubt? See, we can recall what you have studied. After recalling, I will be giving you a simpler method to conclude this. See, we are going to state, or we are going to get the potential energy due to the system of charges. How you can able to get the potential energy due to the system of charges? So here the system of charges is given in the diagram. I am having 3 points, one as A, another one as B, another one as C. On point A, I am having the charges Q1, and point B, I am having the charges Q2, and at point C, I am having the charge as Q3. Now, for this arrangement of charges, I have to go forward. For this arrangement of charges, I have to get the electrostatic potential energy. So, to calculate the electrostatic potential energy of the given configuration, the following procedure is adopted. You just consider all the 3 charges are to be at infinite position initially. First, you have to bring the charge Q1 from infinity to the point A. In that case, no work is said to be done because no other charges are already present in its vicinity. Now, move on to the second point. What is the second one? Now, we have to take the second charge Q2 from infinity to the point B. While moving that second charge from infinity to the point B, this charge Q2, on this charge Q2, a work has to be done against the electrical field produced by Q1. So, to bring the second charge Q2 from infinity to a point B, a work must be done against the electrical field by Q1. So, the work done on the charge Q2 is epsilon is equal to potential multiplied with charge, and the formula is 1 by 4 pi epsilon 0 Q1 into Q2 by R12. This work done, or this potential energy stored on Q2. Work is said to be done on Q2, so potential energy is stored on Q2. Then what is the third one? Now the third charge should be taken from infinity to the point C. While taking the third charge from infinity to the point C, we are having 2 charges Q1 and Q2 in its vicinity. So, a work has to be done on Q3 against the electrical field produced by Q1 and Q2. That is the third point. You see, when Q3 is brought from infinity to the point C, isn't it? When Q3 is brought from infinity to the point C, work must be done against the electrical field produced by the charge Q1 and by the charge Q2. So that work done is total potential at C due to Q1 and Q2, that is V1C plus V2C, multiplied with the charge Q3 or the moved charge Q3. What is V1C? It is potential at C, okay, potential at this point C due to Q1. What is V2C? Potential at this point C due to this Q2. So potential is 1 by 4 pi epsilon 0 Q by R. So V1C and V2C are being written here. After that, you substitute in the above equation, you will be able to get it out as the total potential energy is equal to, what is the total potential? Epsilon is equal to Q3, the charge moved, Q3 into V1C, instead of V1C, 1 by 4 pi epsilon 0, Q1 R13, plus V2C, 1 by 4 pi epsilon 0, Q2 by R23. Now, taking 1 by 4 pi epsilon 0 as common or a constant quantity outside the bracket, taking Q3 inside, 1 by 4 pi epsilon 0 into Q1 into Q3 by R13 plus Q2 into Q3 divided by R23. Therefore, the total potential energy, see, this equation 2 represents the potential energy stored on Q3 because work is said to be done on Q3 in bringing it from infinity to the point. Now, what is the total potential energy due to all the three charges? That is what I have written here. The total potential energy due to the system of charges is epsilon, which is given by or got by adding the two equations 1 and 2. So, by adding the two equations 1 and 2, the final answer that we have got is the total potential energy of the system of charges 1 by 4 pi epsilon 0 into Q1 into Q2 by R12 plus Q1 into Q3 by R13 plus Q1 into Q2 into Q3 by R2.